Welcome to the Problemers Channel Season 2, Episode 44, the episode which I titled Evaporating Watermelons, because in this episode we will solve a problem that deals with the process of watermelons losing their moisture content, and by doing so we will also begin a dedicated study of a new problem-solving approach known as invariant. But before we do that, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, it is a good idea for you to go to the home page of this channel and in the channel's trailer section, find the episode titled The Problemers Channel How To. Watch that episode in its entirety, follow all the instructions that were given in that episode, because in that episode we explain and motivate everything that we do on this channel. In the mathematical problem S2E44, we're told that the 100 tons of the freshly harvested watermelons at the farm A were basically 99% water. Then we're told that the entire harvest of all 100 tons of watermelons with 99% moisture content were loaded, let's say, onto a cargo ship and sent downriver to the farm market at the point B. This transportation of the freshly harvested watermelons took, let's say, several days, and during that time, due to evaporation, the load of watermelons lost 1% of its moisture content, and at the point B, at the destination, at the docks, let's say, the moisture content of the entire load was found to be 98% water. And the question in this problem is the following: how much do the watermelons weigh at the point B at the farm market? And once we know that answer, we can also compute the net loss in the weight of the watermelons in percents, as a percentage. Now, we will solve this problem using a new to us problem-solving approach known in many countries as one and the same name, the invariant. And before we do that, here is a description of how the invariant problem-solving approach works and a sample problem that goes with it. If we want to solve this or that technical and potentially difficult problem using the invariant problem-solving approach, then as a heuristic advice, we should try to do the following. We should try to partition the local material and or process or processes, in plural, into two fairly distinct piles of things. Things that do change or things that do vary in a given context or under given conditions, and things that do not change or do not vary in a given context or under given conditions. And in general and in theory, in vacuum, all things being equal, we should be ready to see the fact that there may be n things that do not change. But again, for example, especially in the Olympic problems, the problem statement is wound up so tight that there is only one thing that does not change, and usually it's quite challenging to find. Either way, as the step number 2, once we manage to somehow analyze the given problem and then partition the material and the processes in this problem into a pile of things that does change and potentially a pile of things that does not change, the heuristic advice here is to step through all the identified things that do not change in a given context and try to leverage that very fact that this something does not change in order to generate the solution of the problem at hand. And again, in the purely academic, let's say, environment, aside from the competitive problem solving, there could be several things that do not change in this or that problem. But in the Olympic and competitive problem solving context, the problem statement again is usually wound up so tight that there is only one thing that does not change, and it is usually a challenge to find even that one thing. The thing or the things that do not change in the given context or under given conditions is usually referred to as precisely an invariant under this or that, or an invariant with respect to. In addition to invariants, there are also these things called half invariants. A half invariant in a mathematical setting is a magnitude that does change in a given context or under given conditions, but that change takes place in a very controlled way, and such a quantity, for example, could only increase and never decrease, or the other way around, a quantity or a magnitude under given conditions and in a given context can only strictly decrease and never increase. And in mathematics, or for example in physics, such half invariants are a popular go-to candidate when it is needed to prove that under given conditions and in a given context, a certain process necessarily or must inevitably terminate in a finite amount of time or in a finite number of steps. Here, amazingly enough, the intersection between the Olympic or competitive problem solving on one hand and the raw textbookish academic environment on the other is quite wide when it comes to the notion of an invariant. And for those who are interested, here is a very short and very tiny smidgen of a sampling of the notion of invariance across mathematics, theoretical physics, and computer science. That's right, if the notion of area can be attached to a planar geometric shape in a meaningful way, then the area of that shape will remain invariant under any isometry of the Euclidean plane or under any composition of such isometries. An isometry in mathematics is just a highbrow term for plain English rigid motion. And the motion is rigid if and only if the distance between any 2 points of the moving object remains one and the same or invariant at all times. To give a straightforward example, if we take our favorite triangle, not so long ago we proved the so-called Heron's formula for the computation of the area of such a triangle, and let's say in any position that we see the triangle right now, we compute the area of the triangle, and then if we rotate such a triangle in the parent plane, or if we reflect that triangle somehow, or if we, for example, translate it in the parent plane in a certain way, and after each such transformation, after rotation, reflection, and translation, we compute the area of that triangle, then that area will be one and the same, or we can actually compose these rigid motions in any which way. For example, in the theory of groups, during the study of the so-called finite dihedral groups, you will see that the rotation and reflection is a very popular composition. Now that you understand how an area of a geometric shape can be invariant under the rigid motion, under the transformation of rigid motion, I suggest that you guys try to think of a different situation when the area of a geometric shape remains the same. For example, as a hint, if we take a rectangle and we put scissors to it, we cut it, for example, into a number of, let's say, polygons. Can it so happen that we rearrange these smaller polygons into a different shape in a certain way, not in an arbitrary way, but in a certain way, and in that way, the area of the rearranged figure will be one and the same. Think about it. Now for the next example of the invariant in mathematics, we will look at the volume. Likewise, if the notion of volume can be attached to a three-space geometric shape in a meaningful way, then that volume will remain invariant or the same under any isometry of the Euclidean, let's say, space. And again, the isometry of the space, just like the isometry of the Euclidean plane, is a highbrow term for rigid motion in that space. And for a straightforward example, I have a model of a regular icosahedron over here, and the fact that the volume of such a solid remains invariant under any rigid motion or under any composition of such any rigid motions means that if we take our regular icosahedron in any position that we see, let's say we compute its volume, a non-zero positive real number, we write that number down, and then we take our regular icosahedron, for example, we rotate it in any which legal way, and after every such rotation we compute the volume of this solid again. Then the number that we will obtain after we rotate the regular icosahedron, for example, will exactly match the number that we wrote down a few seconds ago. Likewise, if we reflect this icosahedron somehow, then after this reflection we compute the volume of this solid, then again that number will coincide with the number that we obtained in our first experiment. And the same way, if we somehow translate our regular icosahedron along a certain vector in the Euclidean space, and then after that translation we compute the volume, that volume will remain exactly the same as the volume that we computed before we started doing our experiment. And the same idea, the invariance of the volume of the solid, will hold if we compose any of these rigid motions of the space. For example, if we rotate, then reflect, and then translate our solid, then the volume of such a solid will again match perfectly the volume of the same solid that we computed before we started doing our experiments. Now, when it comes to invariance, the situation with invariance is rather fleeting and easy to change. And what that means is the following. The context, the condition, or the clause under which a magnitude or a quantity may remain invariant can change at a drop of a hat, which is to say, quite easily. A few seconds ago, we saw that the volume of a solid, if it is possible to attach the notion of volume to such a solid in a meaningful way, remains invariant under any rotation, reflection, and translation or decomposition thereof. But is that the only condition clause or context in which the volume of a solid may remain invariant? The answer, of course, as by now you should understand, is no. There are plenty of situations when one and the same volume will remain invariant under different conditions or under different situations. For example, we can take a mathematical knife to such a solid, carve it up in a careful way, and then reassemble the carved up pieces carefully again in a different solid. But that solid, even though it is different in shape, will have what? It will have exactly one and the same volume. Also, for another example that we saw just a few episodes ago, and here I want to make sure that you guys had the time to take this down. If you did not take this down, then do so now. I'll give you a chance to put this video on pause and go grab a piece of paper and a pen. Okay, wonderful, but now I will erase some of it because as a reminder, as a friendly reminder, in season 2, episode 42, I'll write it down for you guys over here. In season 2, episode 42, we solved the problem S2E44. And remember what the title of this episode was? How a hoof can compute a limit. Exactly. We saw that the volume of a hoof, of the hoof of Archimedes, which looked as follows. It was something like that. And then we had this. And then we had this. And then we had this. Remember this guy? Yes, you do. We partitioned the volume of that solid in two different ways. First, we partitioned the volume of that solid within triangular prisms of varying sizes. And then we partitioned the same volume with, let's say, thin rectangular prisms like so. And by using the fact that precisely under these two different types of partition, the volume of one and the same solid remains one and the same or invariant, we were able to compute a scary looking limit. In other words, we just saw in a span of several seconds that the volume of one and the same solid can remain invariant under three different conditions or in three different contexts: under rotations, reflections, and translations, under carving up and reassembling the carved up pieces back into a different solid of the same volume, or the volume of the solid can remain invariant under the partitioning of that volume with different smaller and simpler primitive parts. For example, if we partition that solid with triangular prisms and we compute the volume of that solid using these primitive parts, and then we partition the same solid with rectangular prisms and we compute the volume of the solid, we will get the answers that match each other perfectly. A polynomial in n variables is called symmetric if and only if the structure of that polynomial remains invariant under any permutation taken from the corresponding finite symmetric group Sn. Here on the left-hand side of your screen, I have shown three polynomials in two variables, and each such polynomial in two variables is precisely symmetric because it remains invariant, or the structure of each such polynomial remains invariant under any permutation taken from the corresponding finite symmetric group S2. And such a group has only two elements. The first element is the identity permutation when x is taken into x and y is taken into y. And the second permutation is called a transposition when x is taken into y and y is taken into x. And as a straightforward exercise, you guys should prove to yourself that if we transpose or swap x into y and y into x simultaneously or uniformly, if you will, then the structure of the polynomial shown here, here, and here will not change. It will remain exactly the same under such a transposition. In order to make sure that you guys understand what is going on with these symmetric polynomials and invariance of the structure of the polynomials under any permutation taken from the corresponding finite symmetric group Sn, riddle me this. This polynomial in two variables, x squared plus y cubed, is this polynomial symmetric? Yes or no? Justify your answer and prove to me, to yourself, and to our community that this polynomial in two variables is what you said it is. How about this one, just for another example? X squared minus y squared. Is this polynomial in two variables symmetric or not symmetric? Yes or no? Again, justify your answer. And here is one more and final example of invariance in mathematics. My final example of an invariant in mathematics hails from the land of the theory of groups. And even if you do not know anything about the theory of groups, I suggest you still listen to what I'm about to say, because this is exactly what you will be doing in your near future. As such, a subgroup H of a group G is called normal. This is the modern term. I'll say a few words about it in a second. It's called normal if and only if it remains invariant under conjugation of that subgroup by all the elements of the parent group G. And it works in a way that is not too complicated and actually quite beautiful, as follows. Let's say G, lowercase g, is any element of a group G, uppercase G. Then the conjugation of an element of a group by another element of a group, let's say we will call it X, is the following product. It will be X times G times the inverse of that element. This operation over here, a compound group product, is called the conjugation of the element G, of the group element G, by a group element X. Evidently, both of these elements belong to the parent group G, and there are some nuances over here. It doesn't really matter, but the people who call themselves the algebraists, they will probably put the inverse on the left and the original element on the right, but here is good enough. So what does it mean to conjugate a subgroup of a group? Well, by the same notation, we will say that, for example, let's write it down over here. If we grab an element X of a group again, then the conjugation of a subgroup of a group by that element X, let's say for now, for demonstration purposes, we'll agree this is a fixed element of a group. It's just one specific element. Then the conjugation of the subgroup of a group G, just like the conjugation of one element of a group, is the following operation. It's quite natural. You can probably construct the answer yourself. What does it mean? It means that we'll apply the operation of conjugation of the element of an element of a group to all the elements of that subgroup. That's all there is to it. In other words, we will write X times, let's say, H1 times X, the inverse of X, and then X times H2 times the inverse of X, and then X times H3 times the inverse of X, and so on, all the way till the, let's say, logically last HM element of that subgroup, taken like so. That's it. There is no mystery. We simply take the operation of conjugation that we cooked up or invented for one group element, and then we trolled that operation through all the elements of a chosen subgroup. Now, instead of keeping the element of the group X fixed, so to speak, we vary X over all the elements of the parent group G. That's all there is to it. In other words, what does it mean to say that the subgroup H of a group G remains invariant under conjugation by all the elements of the parent group G? Well, symbolically, it means the following. X times H times the inverse of X comes out to be precisely H again for all the element X of the parent group G. In other words, if we yank a subgroup H from the parent group G, it will have which structure? Well, not structure, but what will be the content? Element H1, element H2, element H3, element HM, M elements, let's say, for the sake of demonstration in the subgroup H. Then we again take all the elements of the parent group G, throw these elements against this subset of a group G in the conjugate manner like this, compute the result. If the result of this computation comes out again to the set of elements H1, H2, H3, and so on, Hm, then, and that result holds for all the elements of the group, of the pairing group G, then it is said that the group H over here is precisely normal. It will also become the so-called normal divisor of a group and so on. But normal is the word that is relatively new. When I was a kid, when I was growing up academically, these type of subgroups that can be called especially symmetric, if you will, they were actually called precisely that, invariant subgroups. So there you have it, another example of invariance in the textbookish or raw academic setting. For two examples of invariance in theoretical physics, first consider the so-called Kepler's second law of planetary motion, according to which each planet in the solar system orbits the sun in a plane that passes through the center of the sun and in such a way that the radius vector of that planet sweeps out equal areas in equal amounts of time. And what does it mean? Well, first, it means that the magnitude of the linear orbital velocity of a planet is not constant. It varies slightly over time. And when the planet gets further away from the sun, then the magnitude of its linear orbital velocity diminishes a little. But when the planet gets closer to the sun, then the magnitude of its linear orbital velocity grows a little. And that change in the magnitude of the linear orbital velocity of every planet is balanced ever so perfectly according to the Keplerian formalism, that the areas of the elliptic sectors swept by the planet's radius vector in the same amounts of time comes out to be exactly the same. In slightly more detail, it means the following. Let's say we put the planet further away from the sun over here. This is our milepost, and at that point we start our timer that measures a certain amount of units of time, exaggerating for demonstration purposes a lot, of course. Let's say we count 1, 2, 3, 4, 5, boom, we'll look at the planet again, we catch it over here. So this point over here terminates our time measuring experiment. This radius vector over here will be the initial radius vector of the planet. This will be the final radius vector of the planet that corresponds to the measured time delta t. And if we compute the area of the elliptic sector that is trapped between these two radius vectors, then we will get a positive real number, a delta t, which means the area of this elliptic sector that corresponds to the time frame delta t. We write it down, then we give our planet some time to run around, and then we catch it again over here when it's closer to the sun. This is our new measuring point. We start exactly the same timer. Click and we go 1, 2, 3, 4, 5. We measure exactly the same unit of time as we did before. We look at the planet, it's over here, and this will be the initial radius vector of the planet. This will be the final radius vector of the planet. And if we compute the area of the elliptic sector that is trapped between these two radius vectors, then amazingly enough, according again to the Keplerian formalism, that number, a delta t, will be precisely the same as the one that we measured in our first experiment. And in so many words, this is precisely what it means when we say that while the magnitude of the linear orbital velocity of a planet as it traverses the sun over an ellipse does vary over time, the areas of the elliptic sectors swept by the radius vector of that planet in equal times remain invariant over time. Our second and final example of an invariant in theoretical physics is much more highbrow because it has to do a lot with the theorem that was proved by Amy Noether And according to the ME's theorem, which is actually quite fundamental in theoretical physics, if a physical system possesses certain continuous symmetries, then in such a system, inevitably, there will exist certain laws of conservation. Now, asymmetry in physics can come in various guises, but for the purposes of this discussion, asymmetry in physics is the invariance of the structure of the underlying equations of motion that describe the time evolution of a given physical system with respect to a certain transformation. Consequently, a continuous symmetry corresponds to a continuous transformation. And such continuous transformations could be what, for example, rotation of space or parallel translation. Now, in so many words, again, I want to keep the size of this episode manageable. The equations of motion that describe the time evolution of a given physical system are a byproduct of a mathematical object that is called action, which is an integral of another very important notion in physics called the Lagrangian. And the Lagrangian itself is the difference between the kinetic T and potential U energies in the physical system. And in the calculus of variations, this mathematical object, which in physics we call action, is also known as a functional. And consequently, that means that according to M.E. Noether's theorem, if the Lagrangian of a given physical system remains invariant under certain continuous symmetries, it's important to realize here that the symmetries must be continuous. So if the Lagrangian of a physical system remains invariant under certain continuous symmetries, then in such a system will inevitably, there is no choice, there is no maybe here, in such a system there will always exist a magnitude or magnitudes that will be invariant over time, which basically another way of saying that in such a system a certain law of conservation will hold. And it is easy to remember, for example, if the Lagrangian of a physical system remains invariant under translation of space, which basically means we take our favorite reference frame and move its origin from hither to thither. And if we do that, the structure of the Lagrangian does not change. Then in such a system or such a symmetry or invariance of the Lagrangian with respect to a translation of space corresponds to invariance of linear momentum. Linear momentum, which is basically to say that in this case, this particular physical system will possess the law of conservation of linear momentum. If the Lagrangian of such a system remains invariant under rotation of space, then such an invariance of the Lagrangian will correspond to what? Will correspond to the invariance of angular momentum in such a system. And we will say that in such a system, the law of conservation of angular momentum holds. So when we say law of conservation of, this is basically invariance of the magnitude blah over time. And as the final example, if the Lagrangian of the system remains invariant with respect to parallel translation of time, which means instead of measuring the time evolution of a system at the point t over here, we measure it at the point t prime over here. Then the invariance of the Lagrangian in this case with respect to a linear translation in time corresponds to invariance of energy. This is, I'll say, time corresponds to the invariance of energy over time, which is another way of saying that if the Lagrangian of a system remains invariant under translation of time, then in such a system the law of conservation of energy holds. So this is fairly straightforward to remember. Space corresponds to momentum, time corresponds to energy. So as we can see here already we realize that the notion of the invariant is not some flimsy arcane or specialized vehicle that was invented by people who are interested in solving Olympic problems, but this is a well-established or an official citizen in raw textbookish material, if you will. Lastly, I will give you two examples of invariance in computer science, and once you understand what is going on, then I'm sure you will be able to find more such examples on your own. And again, anyone in our audience who knows more such examples, then feel free to share your examples in the comment section. But here we'll start with something straightforward. One example will be called class or type. Class or type. Invariant. And the other example will be loop or cycle. Invariant and computer science, these are popular notions and ideas, and the class or type invariant is basically a certain condition that inhales and reflects the internal state of the object of that class or a structure of that type and remains one and the same or invariant throughout the entire lifetime of the object of that class or the structure of the type, no matter how that object of that class or that structure of that type is manipulated by the external customers. And internally, of course, we want to make sure that when we control the private code, we also do the right thing at all times. For example, let's say in C++ or in Java, we decide to implement a class called soccer field, or in C with a structure and a number of pointers to functions as the members of the structure, we decide to implement the type called soccer field. Usually the standard soccer field size is, if I remember right, 90 meters by 45 meters. So the size of the soccer field that is implemented and kept internally in the corresponding class or structure type must remain one and the same. When we manipulate this field in any which possible legal way, it should never happen that the size of our field all of a sudden becomes 1 by 2 meters or some such. So that is the idea behind the class invariant, and this invariance can get quite involved and complex depending again on the complexity of the underlying object or class. And again, here we like to exercise the KISS principle, keep it simple, stupid, and break things down into as simple as possible, but not simpler components. But this is again blackboard drawing. Real life is much more complicated. The loop invariant again follows the same basic idea, but it is certain condition, maybe logical on some predicates or physical with some data, which holds true on every iteration before the iteration begins and after the iteration completes. So if this is the body of the loop, then before the iteration begins and after the iteration ends, that something for that loop must remain one and the same at all times. Within the body of the loop, the material that goes into the loop invariant may change here and there, but inevitably before and after, that condition must be one and the same and does not change, as the word invariant here reflects. For example, let's say in our loop we maintain two indexes, and it seems that these two indexes vary independently. However, we see that for this algorithm to work in this particular loop with these two particular indexes, it must be so that, let's say, the sum of these indexes n plus m must be always less than or equal certain constant that we somehow define. So these are two examples of invariance in computer science. Again, if you find more examples, don't be shy. Please share with our community your idea in the comment section. Meanwhile, once we now understand more or less what an invariant is in mathematics, theoretical physics, and computer science, let us solve a very straightforward sample problem that demonstrates how the introduction of an invariant into the process of generating a solution will make that solution much more pleasant and much more straightforward. Let us now forget for a moment about the kernels of group homomorphisms and the Lagrangians and come down back to earth and look at a problem that is as simple as possible, that does not require any special preparation, and the only thing that the problem does require is the basic middle school or even lower situational awareness. Let's say that in this sample problem, when the pipe P1 works all by itself in isolation, then it fills the pool of water in X amount of time, xt as shown over here. The pipe P1 working alone filled up the pool with water in X, let's say hours or whatever, and then it stopped working. We drain the pool, and then the pipe P2 starts working in isolation, in solo, all by itself, and the pipe number 2 fills in the same pool with water in Y hours or Y units of time. And the question in this problem is, when the pipes P1 and P2 begin working together, not solo, each one separately when the other one is silent, but together in unison, then in what time tau will these two pipes fill in this given here pool with water? So here, whenever the problem statement is seemingly missing something that we think we need, this is already a signal to us that we will need some auxiliary material that we should be brave enough to introduce and not be afraid to introduce. So what does change in this problem and what does not change in this problem? Well, definitely what changes in this problem is the type of the pipe that works solo while it's filling the pool with water. In the first case, it's pipe P1. In the second case, it's pipe P2. So the types or the type of a pipe that works at this particular moment does change. But what does not change? Correct. Those of our viewers who are paying attention realize that the volume V, let's say, the volume V of our pool that is measured in, let's say, some cubic units of linear measurement, let's say cubic meters. The volume of the pool remains what? Invariant with respect to which type of pipe fills it in at the moment when it works solo. And what does that mean? Well, that means that we can say that the pipe P1, or the speed with which the pipe P1 fills in that volume of water, will be what? Let's say will be S1 times X will produce the volume of water in that pool. Now, the speed is measured in, let's say, just for the sake of argument, in meters, cubic meters per hour, let's say, it doesn't matter. And the time is measured in hours. So our not very sophisticated dimensional analysis squares over here, hour in the denominator here and the numerator here cancel each other out, and at the end we get what? Cubic meters, so everything is good. But because this volume V is the invariant, then it means that is the same volume is filled in by the second pipe in Y units of time, and S2 is the speed or the ability, if you will, in very simple language, of the pipe P2 to produce that many cubic meters of water per unit of time. That's very good. We were brave enough to introduce this invariant symbolically into our symbolic shuffling, and so far we do not know what it is, but we still introduced it, and now we have this two beautiful expressions on the books. Now what? The next key observation over here is the function of ability to fill the pool with water when it comes to these two pipes is what? Is additive. And what does that mean? It means that the rate at which both pipes, when they both work, pipe P1 plus pipe P2, the rate at which both pipes, when they work together, fill in the pool, will be simply a good old arithmetic sum of the ability of the first pipe to fill in the pool with water, S1, and S2, the ability of the second pipe to fill in the pool with water, S2. Not the product S1 times S2, not the ratio, not the arc cosine of S1 over S2, not square root of some other horrible formation. No, it's just the straightforward good old arithmetic sum, and this is it. In a sense, we already solved the problem with the introduction of the invariant, which is what? Which is the volume of the pool measured in some cubic units of measurement. Why is that? Well, from our basic formula that the volume equals S times T, the speed with which a pipe can output water per units of time, and T is the time, follows what? That the rate at which two pipes will be filling in our pool will be exactly what? It will be exactly V divided over tau, and tau is exactly the time that it will take both pipes working in unison to fill in the volume V. That's all there is to it. This is this symbol over here taken from here, S equals V divided by T. And because this function is additive, it simply means from this equation over here what? It means that it is V over X plus V over Y. And this is it. You see, because V is the invariant here, we cancel it out, and what do we have? 1 over tau equals 1 over X plus 1 over Y, and this is what? X plus Y over the product, X times Y. There are all sorts of fancy names for all these numbers formations that you see over here, the reciprocals. But fundamentally, from this equation, what do we have? We see that the time tau is equal to X times Y divided by X plus Y. This is our answer. This is our answer. And look at how straightforward the process of generating a solution or arriving at that answer was the moment we introduced the invariant, which in this case was what? The invariant in this case was the volume of the pool that is being filled by our favorite pipes. Now that we develop a slightly better feel for how we can leverage the use of something that does not vary in the problem in order to generate a solution of the problem, let us go back to our original problem of evaporating watermelons. Whenever people are told that they solved a given problem incorrectly, some of these people go into denial. Some people try to go back and think, did they make a computational mistake, or did they make a much more gruesome and more fundamental logical mistake? And sometimes the embarrassment sets in that, oh my God, I couldn't solve such a simple problem. There is no, again, kernels of group homomorphisms. There are no multidimensional integrals. There are no field extensions, nonlinear differential equations in partial derivatives. None of that. Is just a simple watermelon problem. Put one big watermelon on a ship, sail it down the river, take it off, look at that, what's going on. Still, some people cannot solve this problem, and some students produce a very, as we will see in a few small number of minutes, some very incorrect answers. So Now that we know about the invariant, that this is as we solve more and more difficult problems, and you will develop a better and better feel for how invariant works in problem solving, you will see that it is possible to solve this problem in a correct way, in a very straightforward manner, and when it comes to time, also very expediently. So in this problem, what does change and what does not change? We go back to our description of the heuristic problem-solving approach. We call it invariant, and this heuristic description of heuristic tells us try to partition the material or the processes in the given problem into something that changes, something does not change. So what does not change and what does change in this problem? Well, whenever we have something that resembles a physical process, two things always change no matter what: space and time. Time changes because the clock is ticking, and space changes because things fly and move in all sorts of directions, and there may be many things. A typical middle school case: when the point mass is thrown under an angle to the horizon, boom, we have a different interesting geometry of a point transcribing a certain spatial curve. So here, even in this case, if we know that the watermelons were loaded into a cargo ship and the cargo ship sails from the farm A to the farm market B, we can actually eliminate this physical translation, let's say, from point A to point B altogether. Let's say our 100 tons of freshly harvested watermelons sit idly in the warehouse. What happens then? Well, due to evaporation, it still loses what? Our watermelons lose their moisture content, and they lose the amount of water that they have. So one thing that definitely changes is the amount of water in the watermelons, because initially it's a watermelon is 99% water, and by the time certain things happen, it's 98% water. So far so good. These things change. Now let us think together which things do not change. Awesome, this is a straightforward observation, but since 99, and sometimes it's really amazing how we cannot see the things that hide in plain sight and right in front of our noses. 99 is not equal to 100. And if each watermelon initially at the harvest time is 99% water, then what's going on with the remaining 100% minus 99%, with the remaining 1% of something that sits or present in each and every watermelon? Well, we will call that 1% not water. If 99% is water, then 100 minus 99, or 1% of not water, and that not water, we will refer to it as, let's say, solid substance. Solid substance. And again, in general, when you'll be studying, let's say, higher physics, you will realize that under a proper balance between the internal and external pressure and under the properly set temperature, just about anything can evaporate. Metals can evaporate. For example, mercury evaporates all day long. But in this case, of course, in a very simplified manner, we will take it that the time frame during which the watermelons lost their water content is so short that there is no natural decay and no rot of the solid substance that is present in each and every watermelon. Consequently, we realize what is the invariant, or what does not change in this problem. And here we need to be careful, because here where the sleight of hand begins, and this is where the source of trouble for many students who inventively create all sorts of wonderfully incorrect answers. So what does not change in this case, we argue, is the absolute amount, let's write it down over here, the absolute amount of solid substance in each watermelon is invariant. Invariant with respect to what? Is invariant with respect to time. That absolute amount of solid substance in each and every watermelon, as the watermelons make their way from the farm A to the farm market B, does not change and remains one and the same. In other words, we can, and I'm not joking here, it is perfectly fine to come up with this seemingly silly ideas, but the ones that capture the technical essence of what is going on. Initially, what is being put onto the cargo ship over here? Lots of water plus a little bit of rocks. Rocks do not evaporate. So as time goes by and our precious cargo of watermelons travels down the river from point A to point B, what happens to the water? Well, the water evaporates. Let me show you for the incredible simulation that, let's say now this is the amount of water that we have on our cargo ship, but how many rocks do we have at the point B? We have exactly the same amount of rocks at the point B as we had at the point A. You see, that many rocks were put on the cargo ship at the farm A, and that many rocks came off the ship at the farm market B. This is the invariant, and it is important to understand that this is the, as an invariant, it is the absolute amount of rocks in each and every watermelon. And this is what we capture over here, the absolute amount of solid substance, the absolute amount of rocks. And what is that amount over here? Well, again, of course, you understand by now that you can play all sorts of games with this tonnage of how many tons of, or whatever amount of mass of freshly harvested watermelons we have. But here it follows that we have exactly 1 ton in absolute amount, exactly 1 ton of solid substance, or 1 ton of rocks is a useful and fruitful invariant. The absolute amount of solid substance, 1 ton of rocks. 1 ton of rocks was loaded onto a cargo ship at the farm A, and 1 ton of rocks arrived at the farm at the point B. Now, once you understand this basic idea that the absolute amount of solid substance in each and every watermelon is a useful invariant, you should be able to solve this problem on your own completely. You do not need to wait for me. But I would like to take an opportunity over here, a smaller number of minutes, and share with you guys, for pedagogical reasons, one incorrect way to solve the problem. And amazingly enough, this is actually quite popular incorrect answer to this here problem. A straightforward pedagogical truth is that in mathematics, understanding how, when, and why things do not work is just as, if not more important than understanding how, why, and when things do work, because when the things break down, we get to peer into the fragments of the broken thing and figure out, aha, this is how this thing was put together. So here's one inventive incorrect way that many students unfortunately generate. And again, it, on the one hand, it is always fun to sit back and see how people make mistakes, especially when you know how the problem is supposed to be solved in the correct way. But when you start doing this, you may step on the problem by yourself at all times. So it pays to be always gentle and patient with other people when they make mistakes. So here is the reasoning. There are 3 mistakes in this reasoning, and try to catch all of them as I go along. So some of the students reason incorrectly as follows. First step is actually correct. Let's say 99% of water at the loading docks over here of 100 tons is what? 99 tons correspond to 99% of the initial load of the freshly harvested watermelon. 99%, not written in the fraction notation, 99 parts in 100. So 100th is your unit of measurement. Now they introduce an extra variable, and that is a good thing. WT is the amount or the mass of water, the new reduced amount of water in the watermelons at the point B that is correlated, which is 98%. That's how some students reason. So 98 parts in 100. And this is actually, again, this is the first mistake that you're supposed to catch, because what is the problem here? The problem here is that the students being sloppy with exactly what 98% is applied to. Remember that in some sense, this problem was formulated in such a way that the sleight of hand was injected there on purpose so that the problem solver will be invited to make a mistake. 99% initially, only lost 1% of water, and now it's 98, and it's not really clear. 99 and 98 are very close to each other, and it's very inviting to make that mistake, and sure enough, some students make that mistake. So now they say, okay, WT is the amount of water in the watermelons, which is 98%. And now they make the second mistake. They cross multiply this proportion, and when they do that, what do they have? 99 tons times 98 parts in 100 is equal to what? Water in the dried out watermelons times 99 parts in 100. So dimensional analysis wise, things seem to work. Cancel 100, cancel 100, cancel 99, cancel 99. What is the the mass of water in the dried out watermelons at the point B? Oh, gee, it's 98 tons. Definitely. So the answer is the amount of water in the dried out watermelons is now 98 tons. And when the students are confronted with the question, okay, and what happens to the 1% of not water? Some of the students go, oh yeah, exactly, yeah, you're right. So 98 plus 1 is equal to 99. Yeah, the answer is 99 tons. So it was 100, now it's 99. Beautiful, things work. This is the problem, and they walk away. And this is the third problem that you were expected to catch. What is the third problem over here? Well, the third mistake or the third error in the whole carnival of sloppy reasoning over here is the following. The students who walk away from the problem at this stage, they do not even bother to do a sanity check to see if their numbers actually square with what is given. Okay, let's think. 98 tons supposed to be 98% of what? See, that's exactly where the problem explodes. 98 tons supposed to be 98% of what? Of the new overall reduced net mass of the dried out watermelons. So let's do this straightforward arithmetic. 98% is what? 98 parts in 100. And this 98% is expected to be applied to what? Well, the voice from above, to incorrectly produce number 99 tons. But this is what the students don't do. So if we put 99 over here times 99, then it comes out to what? 98 over 100 is what? 49 over 50 times 99. Pull out your calculator if you want. It will be 97.02 tons, which is no way is equal to 98 tons. This is what we're supposed to get. We're supposed to get 98 tons if we compute 98% of the incorrectly computed overall net mass of the watermelons, which is 99. No good. Likewise, there is absolutely no way that 2% or 2 parts in 100 of 99, which is what? 1/50th of 99, which is what? 1.98 tons, which is evidently not equal to how many were we supposed to have over here? Not equal to 1 ton. How can this be equal to 1 ton? When 2% of the overall, now if the content of the water in the watermelons, dried out watermelons, is 98, then what's the percentage of the not water? 2%. And these 2% supposed to represent what? 1 ton of not water. How is that possible that 1.98 is equal to 1? And how is it possible that 97.02 is equal to 98? There is absolutely no way. This is straightforward sanity check. Also, right away shows that this reasoning is absolutely no good, but some students fail to carry out this sanity check and mistakenly and erroneously think that 99 tons is the answer. And now I will take a short break and erase this material from the board and show how it is possible to somewhat salvage this incorrect line of reasoning. The second mistake that you guys were expected to catch in this faulty line of reasoning was right here. I did not erase it on purpose. Remember that a proportion, a legal proportion, can be constructed only in the case where there is a genuine correlation between all the elements that make up that proportion. But in this sloppy reasoning, 98% is applied to what? Nobody knows. It's a vague and nebulous something, flying potatoes. So as such, the person who did this had no business constructing and cross-multiplying that proportion. That was the problem number 2. So how can we salvage it? Well, now instead of correlations, let's put for example, one way to do it is put the equal sign over here. But now we need to be careful. 99 tons of water in the freshly harvested 100 tons of watermelon represents 99 parts in 100 of what? Of M0, the initial mass, or 100 tons. Consequently, the W kilograms or tons or whatever of water in this case represents what? 98%. And this is where we're being now correct and legal. Represents 98 parts in 100 of what? Of the unknown. You see, that's the correct move right here. The unknown amount of tonnage of the dried out watermelons, the net mass. Now we're on a solid footing over here, and now we know there is a genuine connection or correlation between all the parts involved, because there is over here, remember, there is a ton of rocks that sits in the watermelons at the docks at the port A, and the same 1 ton of rocks arrives at the docks at the port B. Same thing. The absolute amount of solid substance remains the same. So now when we cross multiply this proportion, what do we have? We put 98, let's write this down over here, 99 tons times 98 parts in 100 of X times X comes out to what? W in tons times 99 parts in 100 of M0 of initial mass. Now things look up. 100 and 100 cancel out. Numerically, 99 and 99 cancel out. Here is what? We have 100 tons. We still have 100 tons. 100 tons. And what do we have now? Everything looks good. So now we express the ratio. Let's say we construct the ratio of the number of the mass of water to the mass of the overall. This is measured in tons. The net mass of the dried out watermelons is what? This divided by this comes out to 98 divided by this, 98 divided by 100. This is exactly what it means to be 98%. And yes, now things look legal, because we know that the amount of water, W, in the unknown to us net mass of the watermelons at the point B is 98%, and this is what we said symbolically. But now what? In theory, we have one equation and two unknowns. What are we to do? Well, in general, if we were to proceed that way, we would need to construct another equation that will tie these variables in a way that is independent from how these variables are glued together over here. Maybe we can do that, maybe we cannot, but my suggestion is this: forget about all this dancing with the walls and coming up with all these fancy proportions. All we have to do is go back to the idea of the invariant, which is the absolute amount of rocks in our freshly harvested watermelons. Well, here's a way to circumvent all this difficult reasoning that we saw before and leverage precisely the invariant in this specific problem, or the absolute amount of the solid substance in each and every watermelon. Recall that in a legal proportion there are four pieces: 1, 2, 3, 4. And one way to solve this proportion, this is middle school 101, is to the so-called cross multiply the pieces that make it up. And if right away we know what, if any three pieces in this proportion are known, then the remaining fourth piece can be found trivially and right away. We go back to our invariant, and what do we have? We have precisely four pieces in this problem. The absolute amount of a part, which is solid substance, we know it is 1 ton. Remember my favorite experiment, that 1 ton of rocks goes onto the cargo ship at the port A. One type of rocks gets off the ship at the port B, at the farm market. 1 ton of solid substance is the absolute amount of a part. The relative amount of a part is also known to us. If the new moisture content in the watermelons is 98%, what is the percentage of not watermelon in this load? 100 minus 98 is 2%. Known. The absolute amount of the whole, in other words, the net mass of the dried out watermelon, new amount of water plus the same amount of solid substance, is X tons. And the relative amount of that whole is known to us always, is 100%. We don't even need to think. 100% always in any case. There you go. 1 ton corresponds to 2 parts in 100. And X tons corresponds to 100 parts in 100. There you go. What is the answer? Cross multiply 1 ton times 100 parts in 100 is equal to X tons times 2 parts in 100. 100 and 100 cancel each other out. We move these 2 from here. Let's leave it as 1 over here. We move it over here. 100 times 1 times 100 over 2 is 50. 1 times 50. The answer is 50 tons. Not, most definitely, not 99 tons, as we saw some students proudly produce over here and even fail to run the sanity check over here. 50 tons is the net mass of the dried out watermelons that arrived at the port B sometime later. And so how much do the watermelons weigh now? 50 tons. This is a whopping loss of how many? Before we had 100 tons of goods. Now we have 50 tons of goods. What is the percentage loss of the net mass of our precious cargo? 50%. 1/2 of 100 tons was lost due to the seemingly innocent play of numbers from 99, only 1% into 99. But overall, we lost a whopping 50 tons of cargo. And what is the distribution of these 50 tons? Well, these 50 tons are represented which way? 49 tons of what? H2O plus 1 ton of solid substance. This is our 50. Now, when we go back and we do the sanity check, what do we see? Let me erase this. You get this. This is nothing more than the middle school wisdom. The first couple days in middle school, you were supposed to learn all about it. So here, how do we represent? Let's see. Let's compute the percentage. 49 over 50 times 100 in percentages. So far, so good. This is what? 10. So it will be 490 over 5, represented which way? 450 plus 40 over 5. This is baby arithmetic. 450 over 5 is what? 90. 40 over 5 is 8. 90 plus 8, 98%. And the remaining, what is it? Do we have 1 over, 1 over 49, 1 over 50. Yes, 1 over 50 times 100 comes out to what? 10 over 5, 2% precisely on the nose. 1 ton of solid substance represents 2% of the 50 tons, and 49 tons of water represent what? Represents 98% of 50. So now the problem is solved in the correct way. And sometimes I hear from students, why does it take 1 hour, or why does it take 2 hours to get to the correct answer, to a correct solution, when this is just so straightforward? Well, the answer to that is that it takes 1 or 2 hours to get to a correct solution, precisely because you did not solve this problem correctly, completely on your own, in 30 seconds or less, which is what expected of you. And now, before we wrap up with this problem, let us, sometimes this is also a good idea, to make all the numbers work generically. In other words, what if we take, instead of 100, we will say M0 is our initial mass of the freshly harvested watermelons. W0 is the initial H2O content in this M0, and then WF final is the final content of H2O in the watermelons. So what is X in terms of M, WO, and WF? Compare your results to mine. Wonderful. If you have been following along, then you should have come up with the following result. Initially, we take the mass M measured in your favorite units of measuring mass, for example, in tons. Then W0 is the initial water content in the freshly harvested watermelons. Initially, we take it as percentage. And WF, F stands for final, is the final content of water in the dried out watermelons by the time they arrive at the port B. And then the answer for the total, or the net mass of the dried out watermelons, which includes the new water content plus the old rocks, is given by this formula over here. M0 times the ratio of 100 minus W0 and 100 minus WF in the denominator. Numerator, denominator. Here, once we reduce it to this computation, we remove the percentage sign. So these are just the numbers as I showed over here. These are, let's say, for the interesting case, strictly positive real numbers between 0 and 100, exclusive. And the condition, of course, the interesting condition is when the final number is less, strictly less than the initial number. And once we plug these numbers into this formula, our numbers, M0 is 100 tons, W0 is 99, WF for final is 98, 100 minus 99 is 1, 100 minus 98 is 2, 100 times 1 over 2 comes out to 50 tons, in agreement with the previously obtained result. And one side effect, or a benefit of doing solving the problem as general, is now we can plug in various numbers and analyze how does the net mass of the dried out material of dried out watermelons behave when we vary numbers over here, the initial content, the final content, and the amount of the freshly harvested watermelons. But again, one more time, I want to emphasize the case that the loss of the net loss of the precious cargo from 100 tons to 50 tons is actually quite surprising for many people. And that also explains one more time, or justifies, why I titled this episode Evaporating Watermelons, because if you run this kind of business, this is also translates to evaporating money out of your pocket. And finally, before we call it a day with this problem, one more thing I wanted to say is that the people who figure out how to solve this problem very quickly in 30 seconds or less, they see that exactly again, 1 ton of where was it? I erased it. That 1 ton of solid substance, in other words, 1 ton of rocks. 1 ton of rocks used to be 1/100th of the overall cargo, and by the time that cargo dried out and arrived in the port B, it became what? 1/50th. So 1 is 1/50th. It means that without any fancy proportions in your mind, without pen and paper, in 30 seconds or less, boom, 50 times 1, 50 tons is the answer. Problem solved. But again, solved why? Solved precisely by leveraging the idea of the invariant. Now, this is it for the mathematical problem S2E44, and we will move on to a new challenge next. In our next challenge, the mathematical problem S2E47, the setup is the following. We have a magic tree on which there grow 2 types of fruits, a banana and an apple, a bunch of bananas and a bunch of pineapples. Let's say this is a mathematical garden, and once you walk into that garden and start picking the fruits from that tree, you have to pick exactly 2. You cannot pick 1, you cannot pick 3, you cannot pick 15, and you cannot pick 0. You have to pick 2 fruits. So if you pick 2 bananas, banana and banana, or if you pluck a pineapple and a pineapple, then either one of these 2 fruits are replaced with 1 pineapple. In other words, you pick 2 bananas and then magically 1 pineapple grows back. Or if you pick 2 pineapples, then magically 1 pineapple grows back. And we're also told that if you pick different fruits, 1 banana, 1 pineapple, yank, yank, pluck, pluck, then in their place there will grow only 1 banana. 2 different fruits, 1 banana grows back. So someone was collecting pineapples and bananas that way, and in that process it so happened that 1 fruit was left over. 1 fruit was left over. The challenge is to figure out which fruit was left over, a banana or a pineapple. And again, of course, no one cares about the actual answer. We want to know why, the justification, and how you arrived at that answer. If the number of bananas and the number of pineapples on the tree before someone started plucking them was known in this experiment. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will share my solution of the mathematical problem S2E47.